All right, so for this section, we are going to be working with L'Hopital's rule. And what we're going to do is we're going to see what happens if we have a function and we try to apply the limit. Mostly going to be working with a rational function. If we apply the limit and we get what we call an indeterminate form, then we're going to be able to apply this rule. All right, so for instance, let's say we had this example here. Okay, so normally what we would try to do is we would go ahead and simply try to evaluate this limit. We can see here x is approaching 0, and so we would just simply would replace every x we see with a 0. Okay, well, let's see what happens if we did that. Okay, so of course, plug in a 0 here. That's 3 times 0, so 0. We would have e to the 0 minus 1. And then, of course, plugging in 0 here, we get 0 in the bottom. Then this e to the 0, we know anything to the 0 power is 1, right? And so what we end up getting is 0 over 0, okay? We call this an indeterminate form, okay? So that means we're not able to evaluate that, okay? So anytime we get 0 over 0 or infinity over infinity, anything of that nature, then that's when this nice L'Hopital rule comes to play. So what the rule says is we need to find the derivative, all right, of your top function. So let's say this is f of x and let's say this is g of x. Then what we're going to do is find the derivative of our top function, find the derivative of the bottom, and then see if we can evaluate it after we find the derivative, okay? All right, so let's say that we want to take the derivative of e to the 3x, okay? So of course, let's just simply take the derivative of the exponent, which is 3, and then just rewrite your function. And then of course, the derivative of 1, well, that's just 0. And now let's take the derivative of the bottom, okay? So of course, the derivative of 2x squared is just simply 4x. And then, of course, the derivative of 2x, that's just 2, okay? All right, well now, okay, and don't forget, we have to keep this limit in front every single time. Okay, so I'm going to just stick my little limit right here. Okay, so now let's see if we can evaluate now. Okay, so we're going to plug in a 0. Okay, again, to every x we see. Okay, so what are we going to get? 3 times e to the 0 over 0 plus 2. Well, then here, this is just 3 times 1, then just 2 in the bottom. So there we go, right? We were able to actually evaluate that and get an actual value now, okay? So therefore, we say that this limit here is just simply equal to 3/2. All right, so let's take a look at this example, okay? This time we have x is approaching pi over 2 from the left, okay? So it's kind of hard to see that little minus there, but it's approaching it from the left, all right? So again, the first thing we would do is always go ahead and try to do our direct substitution. So you can see if I were to plug in my pi over 2 here into my x in my denominator, what do we end up getting if I plugged in a pi over 2 there? You can see the 2's cancel out, so I end up getting pi. So in the bottom, right, we got 7 over pi minus pi. Well, that's going to be 7 over 0, right? So we know we don't quite like that, right? And then what happens up here at the top? Okay, well, if you think about pi over 2, right, at the top of the unit circle, we know that what's happening here is really undefined, right, because we know we have an asymptote at pi over 2 when we are referring to tangent, okay? And if we were to look at the graph, we're really approaching it from the left side, and so we would see, okay, well, what's happening there, all right, we would end up getting infinity, right? So here, 7 over 0 is infinity. We get infinity over infinity. Well, what does that mean? This is also considered to be an indeterminate form, okay? So that means we're not able to evaluate it just yet. So anytime we get that kind of form, we know, well, we can now conveniently, right, apply this L'Hopital's rule, okay? So what we're going to do first is we're going to see if we can rewrite our function, okay, just to kind of help us with taking a derivative, okay, so let's rewrite our function. So of course this tangent is understood to be over 1, So we can rewrite this as tangent times the reciprocal of the bottom, okay? And so I'm just going to kind of rewrite it with my 2x minus pi in the front times my tangent x, okay? And then all of that is over 7. All right, so now that we have it rewritten, let's now see if we can put our limit now in front of that, okay? So we're going to write the limit as x is approaching pi over 2 from the left, and then just simply rewrite our function the way we have it rewritten here above, okay? So now what we're going to do, since we got this 7 here, how about we just kind of pull that out to the front so it's really 1 over 7, right? Just pull the constant out. And now what do we have left? Just 2x minus pi times tangent x, okay? All right, so now what we're going to do is we're going to see if we can rewrite our tangent in terms of its reciprocal identity. So that means we got 1 over 7. The limit as x approach pi over 2 from the left. And remember, the reciprocal identity for tangent is just 1 over cotangent, okay? So we're going to see how that's going to help us, okay? So now we're going to rewrite it like so, okay? So now let's see if we are able to apply our direct substitution, okay? So let's apply the limit and see what happens, okay? Well, similar to what we did before, if we were to go ahead and replace this x with pi over 2, well, what's going to happen? Okay, same thing that we had up here. So we're going to end up getting a pi minus pi in the numerator. Okay, well, we know that's simply going to be 0. Okay, and then if we were to try and plug in our pi over 2 into the cotangent, right, then we're going to see again that we're going to end up with another indeterminate form, okay? So therefore, what does that mean? Okay, so anytime we get another indeterminate form, then that means, okay, we got to keep applying this L'Hopital's rule. We're going to have to take the derivative again, okay? So let's take the derivative of our numerator. So of course, the derivative of 2x is just 2, and then of course the derivative of pi is just a number, so that's going to be 0. So we're just going to get 2 in the numerator, and then take the derivative of your cotangent. Well, remember our derivative rules. The derivative of cotangent is negative cosecant squared x. All right, so now once we find that derivative, let's now go ahead and do our direct substitution, okay? So if you want, you can rewrite this since we got that square in the bottom. All right, if you want, you can go ahead and rewrite that as cosecant x and then with the square on the outside, okay? So let's apply our direct substitution, okay? Well, we have that 2 in the numerator, right? There's no x to plug in for, so we know the top of that is just still going to be 2. And then the bottom, we have this negative. Okay, so at the times here we have a negative because of this negative. And now let's see, we would then go ahead and plug in pi over 2 here into the place of our x, okay? And remember cosecant, that's reciprocal is sine. So if you try to do your sine of pi over 2, well, you'll see that it's actually going to be 1, okay? Then of course we have a square on that. So let's see if we can put it together and simplify it down, right? Remember this negative here is on the outside of the square here. So we end up with 7 times negative 1. So then putting it all together, and for your final answer, you end up getting negative 2 over 7, okay? So therefore, we're saying that our limit here is equal to negative 2 over 7. All right, again, let's see if we can try out that L'Hopital's rule, if it's convenient to apply it for this one. So again, anytime you have your limits there, you want to go ahead and apply your direct substitution. So of course, if I were to plug in 0 into my denominator, you're definitely going to see you're going to get 0 for all of that in the bottom, okay? Well, what do we get here? Plugging in e to the 0, plugging in 0 here. Well, what do we know sine of 0 is, right? That's just 0. And then we have this 1 at the end here, that's minus 1. So put it together. We know e to the 0, well, that's just 1. And then we have this, of course, minus 0 up top, and then another minus 1. Well, what do we end up getting, right? We get 0 over 0. So again, we have an indeterminate form. So we know, yep, we now are able to apply L'Hopital's rule, okay? So remember the rule says to find the derivative of your top function and then find the derivative of your bottom function, okay? So find the derivative of e to the x. Well, we know that's just e to the x. Then the derivative of sine, well, that's cosine, and then of course the derivative of the minus 1 would be 0. So we just have e to the x over e to the x minus cosine x in the numerator. Now let's take the derivative of all of our terms here in the denominator, okay? And so when we do that, we end up getting 4x cubed plus 18x squared plus 30x, okay? So let's see then, are we able to apply our limit, okay? So again, x is approaching 0, so every x we see, we're going to plug in 0. All right, well, what is that going to do? Well, here, of course, that's going to be 1. Well, what is cosine of 0? That's actually 1. So we get 0 in the numerator, and of course, we're going to get 0 in the bottom for all of those x's. So what does that mean? Still in indeterminate form, so that means we have to find the derivative again. Okay, so keep going until we're actually able to evaluate the limit, okay? So what is the derivative of e to the x? It's e to the x. What is the derivative of cosine? This negative sign. And then in the bottom, take the derivative of each of those terms. 12x squared plus 36x plus 30, okay? All right, since we have a minus here, if you want, you can go ahead and just rewrite a plus and the numerator, so e to the x plus sine x over 12x squared plus 36x plus 30. All right, so let's see. Are we ready then to apply our direct substitution? So every x we see, let's plug in 0, okay? All right, so what are we going to get? Okay, so e to the 0 up top plus sine of 0, okay? Then, of course, with the 12 and the 36 here, they both have the x, so that's going to be 0 plus 0. Then we got the 30. All right, e to the 0, well, that's just 1. And sine of 0, well, that's 0. And then in the bottom, we have 30. So there you go. Okay, we were actually able to evaluate that and find an actual value for that limit. Okay, so this limit is equal to 1 over 30.